Thanks. Okay, welcome to my talk about the Angular compiler and especially what we changed in Angular 4 in the inside. So just a heads up, this talk is about the internals of Angular, what the compiler does. So it's not something a regular user needs to know, but it might be interesting for you to know if you want to create PRs for Angular or if you just want to know what's going on. So you probably heard that. Igor mentioned it. In Angular 4, we did something to make your application smaller. And there were tweets about it. Okay, I upgraded to Angular 4, and it reduced my bundle size from 2 megabytes to 1.38 megabytes. That's cool, right? So what actually happened underneath? To understand that, let's make a quick overview what the Angular compiler does. So the Angular compiler takes all the metadata you write in form of decorators, takes all your templates, takes all your style sheets, and it analyzes them. You can call this parsing. Then it builds a tree out of it. It's called abstract syntax tree. And from that tree, it then creates TypeScript code if you use ahead-of-time compilation, or JavaScript code if you use just-in-time compilation. Once we have that code, then we take this code, and this code actually instantiates your application later on. Like it puts everything together, it news up your components, and it instantiates the templates. So what did we change? This architecture did actually not change. The things that we did change was the way we generate code, what kind of code we generate, and then later on how this code instantiates your application. So let's make some simple examples to understand what's going on. So let's assume we have a hello component, and it uses a template like this. So there's an element inside, a div, has an attribute and a value. And then we generate this kind of code. So if you used ahead-of-time compilation, you know these files that we generate. They're called ng-factory.ts. That's the files that we produce. And they now contain a function per component. They use the component name as prefix and a suffix, in this case view. And this function returns something. It calls another function, in this case viewDef. That's a helper function which produces a plain old JavaScript object. And that helper function, or this data that's returned, has a type. And I put that type here on that side. So the viewDef itself is just an object that contains a property called nodes. And then inside of the viewDef, we can put different nodes inside. So one of them is an element. There's a helper function elementDef, which again just creates a plain old JavaScript object, and it has this shape. So there's an element property inside, name property on it, and attributes on it. We are using these helper functions because that's actually shorter than to put the object literals there. And it also minifies a lot nicer. You can, if you run this through Uglify or something, it just shortens these function names to A, B, and C, and then it gets really compact. Okay, so that's elements. Okay. Another thing you need to know about this is that the view definition for a component is only created once. So per component class, we create one view definition, and then when we instantiate your component, we create a so-called view data out of it. So the view data links to the view definition, and it contains the runtime nodes. So if you have an element def, you instantiate it, you get out an HTML element, and so forth. So we do this separation to make the many instances of your components relatively small in memory usage. So everything we move into the definition, where there's only one instance, and everything else that needs to be created multiple times goes into view data. Okay, that's simple. Let's have a look. How do we represent a hierarchy of elements? There are various ways of representing trees. We chose the following. So we say view definition takes an array of nodes. It's a depth first order of nodes. And the first argument to this element def is the number of children. So if you think about it, you've got a tree, and if each node knows how many children it has transitively, then you can put all the nodes in an array, and it still defines your tree in a unique way. So then it's clear who's the child of whom, and we can use that to instantiate your application in the right way. So we have a new property child count. on the node dev. Directives are a little more interesting. So for directives, you always have two things, right? You have a template. In this case, we've got an input and an attribute on it, ng-model. And you have a class that's annotated with @directive. It has a selector on it. You might have DI dependencies. ng-model, in this case, takes an ng-form as dependency. And then our generated code looks like this. There's another helper function called directive def. Let's ignore the 3 for now. ng-model is the constructor, and ng-form are the dependencies. And this also desugars into a plain old JavaScript object that's noted here in the node definition with another attribute directive. So what is this 3? How do we get to 3? 1 plus 2 is 3, right? That's simple. So it's related to lifecycle hooks. So if you look at the real implementation of ng-model, it's actually more complicated. It's not just a class with one constructor. It has lifecycle hooks, ng-on-changes, ng-on-destroy, and many other things. But these lifecycle hooks, we need to know. So because it's something where Angular calls you back when a component is destroyed or when changes happen. And that's what we use this 3 for. We use a bitmap for, we call them node flags, which are interesting things to know about a node. And then we just combine them. And as the first bit, we use on changes. The second bit is on destroy. And if you sum them up, you get 3, right? It's just a compact form of representing this. Again, our goal is code size. And the last part are bindings. So let's say we have an anchor element, and we bind to the href property on it, and we set some value, some href on it. Then we generate the following code. So element def takes another argument, which is the names of the bound properties. In this case, we bind href. And our node def also takes a structure that stores that name. The other piece we add is that a view definition has an update function. This update function will be called on each change detection cycle of Angular. And you probably know change detection is something that happens very often. Whenever there's an event, Angular change detects all of your components. So this means whatever we do in this closure down there should be better fast, because otherwise it will slow down your whole application. And what we do there, we call a check function that we pass to the update function back with the values of the bindings. So the update function gets the view data, the component, and this check function, and then it calls the check function with the view data again, with a node that contains the bindings, the index of the node. In this case, there's just one node, so index is 0, and the values of the bindings. In this case, we only have one binding, so there's just one value. But essentially, we take the expressions from your template and translate them to one expression in JavaScript code. It might get a little more complicated. You see we added like comp dot before it, because in JavaScript, you need to have a context, what you evaluate against. Otherwise, you would read a global variable, which you don't want in your template, right? Like it's a little transformed, but one expression in your template becomes one expression in the generated code. Okay. The last thing we need for bindings is the old values. You probably know bindings in Angular only fire if something changes. So if you have a binding on your directive or on the DOM, we only set it if the value actually changed. So we need a place to track the old values. And we do that in the view data with an array of all the bindings of all the nodes. Okay, so what's the difference between Angular 2 code generation and Angular 4 code generation? Angular 2 we know, Angular 4 we know now. Let's make the example a little bigger. Let's say we have an input element with an ng-form binding. Previously we just had a property on it, just an attribute. Now we have a real binding on it. And ng-model has the lifecycle hooks, as we said. We've got a dependency, and we've got an input property. Angular 4 looks like this, the generated code. So directive def also takes a fourth argument with the properties that are bound, similar to element def. And we have this one call for the check function. Angular 2 is a little bigger, and it's a different principle, if you think about it. Angular 2, we generate a class per template, And in the constructor, this class, when we new it up, immediately creates all your elements, all your directives, and stores them in properties. So that's a little different. In Angular 4, if I call this view definition or this function hello view, it doesn't do anything. It just produces data, right? But there's nothing that happens. Compared to Angular 2, when I new this up, things already start to happen. Angular 2, it's also really nice that we don't use any arrays there. We don't use data structures. Like, this is really good in terms of performance. Like, maybe you saw my talk at Angular Connect in last autumn. I argued for this is the way how everybody should do it. You should just use properties and no arrays whatsoever. It also has some nice features. You can set breakpoints everywhere. You see what happens. It's really nice. The only downside is it's big, right? And that's why we made this change to this other architecture. And in the end, it's a trade-off that we have here. So if you think about performance in a more general sense, there are multiple metrics that you try to optimize. So we've got the size, we've got bootstrap time, we've got routing time. This means you have a view in your application, you destroy it, you go to a different view, and we've got update time. This means this view stays, you just update all the values. And usually what happens, and what happened to us, is we focused on one of these metrics, for example, update, and we said, okay, let's make updates super fast. And we did. But then other metrics suffered. And now we dialed this thing a little in a different direction to say, okay, we want to optimize size. And if we regress in the others a little bit, it's fine. If you can make size a lot smaller. Right? It's always these trade-offs that you want to make. And how do we know that it's the right trade-offs? So we have benchmarks. So I will show different benchmarks of different applications for these different aspects. So the first is the size. So that's an example application that we use internally. You can see how the size varies over time. This first bigger bump, that was Angular 4 release candidate 1. And this later bump was release candidate 3, so also before final. So you see, we didn't get it right the first time, there were increments that we had to do. This application was improved by about 20%, minified size. It's not a lot, but that's also using Closure Compiler. If you were already using Closure Compiler externally, you would see less impact of this change that we made. Because Closure Compiler is super good at optimizing your application. It renames properties and everything. But everybody externally uses Uglified.js probably, or something similar, which cannot rename properties. And there, this impact is a lot bigger for code size. And this was also our goal, to support users that don't use Closure Compiler, because it's really hard to use, actually. OK, so we measured the size. It was good. Then we measured the bootstrap time for this application. So bootstrap here is excluding network time and excluding JavaScript time, JavaScript parsing time. So V8 parsed everything, and then it created the first view. How long did that take? And as you can see, there was no regression for this example app, which is really cool. It was a little counterintuitive. I would have thought, because we need to create these view definition objects, right? It would take a little longer, but it didn't. It was interesting. So it's the best thing you can do if you try something to optimize performance, do benchmarks, and then you'll know. So that's bootstrap. Routing time, again, that's destroying everything, creating everything again. We actually had a regression. So the blue one is our baseline. That's without using Angular. Green, that's an Angular application. And we regressed from 40 milliseconds to 50 milliseconds. That's about 20%. That's huge, right? But if we look at this application, that's our so-called tree benchmark. The tree benchmark is a binary tree of depth 11. So we've got 2,048 nodes components in there, but they're super simple. They just use itself recursively. So there we had a regression. So then we said, let's actually look at a more complicated benchmark. The ng-switch tree, that's the same, also binary tree, but it uses an ng-switch in each component. And there we actually did not see a regression. And if we go to our example app, which uses the real router to destroy a view and create the other view, we also did not have a regression. So it's interesting. So for very, very simple components, we have a regression, but for more complex ones, we don't. And so we said, okay, that's probably okay. If we get like a big chunk of code size eliminated, then that's okay. And for update, it's the same story. Here, we are actually faster than our baseline. So blue is our baseline. And green, that's the Angular 2 application. And you see we jumped from 6 milliseconds to 8 milliseconds. That's also quite a bit. This bump in between, that was actually an error in our measuring infrastructure. So these are real numbers, right? It's not fake. And we fixed it after we introduced the view engine, and that's why it bumped up. But like, ignore this, it started at 6, it went up. But there's the same story. If we go to the ng-switch tree, we also see this bump, but ignoring that, like, there's no regression in there, which is super cool, right? So to summarize, we made a big impact on size that you saw on Twitter and everywhere. Bootstrap time stayed the same. Routing time stayed the same for non-trivial components. That's why the star is there. And update time the same. For non-trivial components, it should be about the same. What's next? So the biggest thing that will change with the Angular compiler is not the compiler itself, but that we will make AOT the default, ahead of time compilation. It was mentioned multiple times, but we really believe that's the way to go. To make this actually happen, there are several things we need to do. So one thing, we need watch mode. You probably know TypeScript. You can run tsc-watch. We want to have the same for our ngc. So you can do ngc-watch and integrate it with our Angular CLI. Like, it should be immediate that you get the feedback. So that's good, so you get a fast round trip. The next thing, we need better error messages. I agree with Hans, totally agree. We should always have like source line, source column of the thing you need to change. And the messages themselves should be better. Then another thing we will actually work on is type checking in templates. So maybe you saw, if you use ahead of time compilation and you misspelled a property, then there will be a type check error in your ng-factory file. But if you're not an expert, this doesn't tell you anything. Because like looking at these ng-factory files, you don't know like what Angular does under the hood. So we will change this to be a type checker that will report errors regarding your template. So it will say line 2, column 3, in this and this HTML, you made a mistake in that property. And it will actually work with, if you use TypeScript, strict null checks, it would also work with strict null checks. So for example, you say, I have a content child, and it's non-nullable, and then if a user uses your component and does not give you a child that matches, you will get a type check error, which is like super cool. So Chuck, on our team, he's working on that. I'm super excited for that. Two more things. So one is we want to make the metadata more flexible. And I think everybody who used AOT experienced this. You write a provider, you say use factory, you put a closure there, and then AOT will complain. Because it only allows top-level functions as factories. But we will change it so you can actually use closures there. And the last part, we will actually remove the ng-factory files altogether. So we will change our compile pipeline to inline them into your code while we compile it. So and then in the end, like this matches the theme Igor said this morning in the keynote. It will be a lot simpler to use the Angular compiler. It's less concepts you need to know. It's just simpler to use. Thank you.